So this third lesson on implicit differentiation is really just focused on looking at working with the derivatives of the inverse trigonometric functions and using it with implicit differentiation. And so earlier on the course, we introduced, well, not really introduced, to be honest, you were introduced to inverse trigonometric functions when you first learned about trigonometry. Inverse sine, inverse cos, inverse tangent, but they're more or less buttons on a calculator. It's probably how you understood them. Earlier in the course, we worked with these functions a bit and understood how they are, arc sine, for example, is the inverse of just a particular interval on the sine function. And same thing for cos, and arctan. Well, what we have here now are the derivatives of these functions. And to be honest, the most important part of knowing these derivatives actually comes into play when you learn about integrals, but we have to be introduced to it here. So we're not going to work with the derivatives of inverse functions a ton, but they become really important when dealing with integrals. That said, you do want to become familiar, from memory of these three derivatives. The derivative of arc sine is 1 over root 1 minus x squared. The derivative of arc cos is the same but negative. And the derivative of arctan is 1 over 1 plus x squared. Notice the derivatives of these three inverse trigonometric functions are not themselves trigonometric functions. And with that said, though, let me prove that the derivative of arc sine is indeed 1 over root 1 minus x squared. And as always, when I show a proof, the idea is not that you need to memorize this or anything, just to kind of show where it comes from. So first, let's start with arc sine. Y equals arc sine of x, which I can rewrite as x equals the sine of y. Right? That's what an inverse is, right? Your input and output are independent and dependent variables are switched around. But remember, arc sine is only the inverse of a region of sine when the input is between negative pi over 2 and positive pi over 2. And since if I write y equals arc sine x as x equals sine of y, which are equivalent, y is the input, and so this is only when y is between negative pi over 2 and positive pi over 2. And that's the difference between the inverse of sine and arc sine. Or the inverse, the true inverse of sine, because sine is not 1-to-1, would be something that's not a function. So again, when we deal with arc sine, or that button on your calculator, we're dealing with just the inverse of sine between negative pi over 2 and positive pi over 2 for inputs. Okay, and again, this is I'll just make a little note here. This is from Unit 1. So if you need to refresh yourself on that, please do so. With that said, now I want to differentiate x equals a sine of y with respect to x. So I want to implicitly differentiate x equals a sine of y by differentiating both sides with respect to x. Oh, I want a skinnier marker, actually. Okay, and now that I look at this, the left-hand side, the derivative of x with respect to x is 1. Oops. On the other side, the derivative of sine y with respect to x, knowing that y is a function of x, I have to use the chain rule. And so for this, the derivative of the outside function will be cosine of y, and all of that times the derivative of y, which is y prime. All right, which I'm trying to figure out y prime. Right, I'm trying to figure out the derivative. So if I isolate y prime, I get this. One over the cosine of y. And notice, I'm actually getting pretty close to what I'm trying to prove. I'm trying to prove that the derivative is 1 over root 1 minus x squared. So somehow we have to go from cosine of y to root 1 minus x squared. So how do we do that? Well, first, by using one of our identities for trigonometric identities. And so I'll make a little note here. So note, the Pythagorean identity is that sine squared plus cos squared equals 1 for any input. So in this case, I can say sine squared y plus cos squared y must equal 1. Which means if I solve for cos squared y, I know that must equal 1 minus sine squared y. And if I solve for cos y, not cos squared, I square root both sides. So this must be plus or minus the square root of 1 minus sine squared y. However, I got that plus or minus there. I'm getting really, really close to what we're trying to prove. If you look back up here, I'm trying to get the root 1 minus x squared, not plus or minus. And I'm getting close, but I got that plus or minus here. So how do I know in the end it's just the positive? And this is how I know. And we need to note the restriction that I mentioned earlier. Note the restriction on y is only from negative pi over 2 to positive pi over 2. And those intervals, keep in mind this is really, if you think about an angle in standard position, this is from quadrant 4 and quadrant 1, and those two quadrants, negative 90 degrees and up to positive 90 degrees. In those two quadrants, cosine is always positive. So I can rewrite this expression up here as cos y equals just the positive 1 minus sine squared y. And again, what I have there written in red all comes back to this restriction right here. Again, arc sine, the inverse of sine is only the inverse of part of sine, where the input is between, in this case the input is y, is between negative pi over 2 and positive pi over 2. And in those quadrants, cosine is always positive. And that's how I know, looking at this equation, I only want the positive form. So now I can put that back into my derivative up here and say y prime equals 1 over the square root of 1 minus sine squared y. And all that's left now, because notice I'm so close to what I'm trying to prove, I'm trying to get to this right here. I'm so close. In the end, there has to be a way to show that sine squared y is the same as x squared. And I can show that actually quite nicely if I just look back right here. Notice, one of the first things I did was write y equals arc sine x is x equals the sine of y. For all of this we have here, x is equal to the sine of y. It's the first thing I wrote down. So sine squared y must be the same as x squared. And I'm done. Okay, that comes back actually. Oh, what color should I pick? Oh, what a lovely pink. There we go. And that comes back from what I have up here. And there, I've proven it. I'm not saying it's easy, and again, like I keep saying, the point of these proofs is not for you to memorize them, but quite often, there's very few proofs in this course that we don't actually have enough skills already to get to. Okay? With that said, you could do something similar for proving the other derivatives of these inverse functions, so I'll just leave it at that. With that said, really the most important part now is to use these. One more comment though. These are the derivatives here of the these are the derivatives of the inverse reciprocal trigonometric functions. That's a lot of words, right? So the derivative of arc cosecant, which is the derivative of the inverse of the reciprocal of sine, that's a lot of syllables, is what you see here, negative 1 over x root x squared minus 1. In general, though, these are not nearly as important as the other ones, and so you do not need to memorize these. Anytime you have homework questions that involve these, just reference your notes. These are your notes. If I were to ask you something like this on an assessment of some sort, I would give you this part. Okay. So with that said, let's now use this a bit. And so I want to find the derivative of y equals the arctan of x squared. And so the key here is hopefully we realize we need to use a chain rule, because we have a quadratic function inside an inverse trigonometric function. So first, to find the derivative, I differentiate the outside function. And the derivative of arctan is 1 over 1 plus the input squared. In this case, the input is x squared. So x squared squared. That said, I have to use a chain rule, so now I have to multiply by the derivative of the inside function. And the derivative of x squared is 2x. And so I might as well just clean this up since it's pretty straightforward to do. In the numerator, I have 2x. In the denominator, I have 1 plus x to the power of 4. And so before I go on, chances are you may have been a little thrown off by this part right here, the x squared squared. But if I go back to way up here, okay, well, you have here the derivative of arctan x is 1 over 1 plus x squared. But this was the derivative of x squared. So the input was x squared, so that's why you have x squared squared. All right, I think I just have one more example. Is that it? Oh, two more examples. All right, same idea. I want to differentiate this. Again, I need to use a chain rule. Honestly, it'll be very rare we don't use a chain rule for the rest of the course on pretty much every question. Not quite all of them, but the vast majority, well, the chain rule will come up. And so in this case, similar to before, I have the inside function being a radical function this time, the outside function being arc cos. And so first I want to differentiate arc cos. That's a bit more space. So the derivative of arc cos is minus 1 of root 1 minus x squared. If it was arc cos of x, but it's arc cos of root x, so it's 1 minus root x squared times the derivative of root x. Which that said, I'm going to erase that in a moment. What I have, nothing here is wrong, but the derivative of root x is the same as the derivative of x to the 1/2. And the derivative of x to the 1/2, I can use a chain rule, is 1/2 x to the negative 1/2. So not the chain rule, the power rule. So instead of me writing this out a whole bunch, I'll just write it like this. All right, and so now it's just a matter, I am done. It's just a matter, I might as well clean this up a bit. So my denominator, I have just negative 1 over 2 times the square root of 1 minus x times the square root of x. Right, all of this here is the same as this part. And if I'm going to do that, again, nothing wrong with this, but I have two radicals being multiplied to each other. I might as well put them together. And so I can put this as 1 minus 1 over 2 times the square root of x minus x squared. Keep in mind, again, most of my work was actually not differentiating. Most of my work was working with radicals and negative exponents and whatnot. Really important things. There really wasn't a lot of steps to my actual differentiation. I really was done right here. All right, last one. And if you haven't done so already, for other ones, I would definitely at this point, since this is the last one, I would pause the video. I would try this before I try to do anything. But again, you want to differentiate. You want to find dy dx of sine x equals arctan y. So notice this is an implicitly defined equation. So not surprisingly, you'll use implicit differentiation. But I would definitely try this before you watch me work through it. Okay, so the first thing I want to do is differentiate both sides with respect to x. All right, left-hand side, pretty straightforward. The derivative of sine x with respect to x is just cos of x. The right-hand side, we have to use the chain rule again. And so first, the derivative of arctan is 1 over 1 plus, in this case, it'll be y squared, but times the derivative of the inside function, which is just y prime. Right, and just like that, I'm just about done. It's really easy for me to isolate y prime. And so y prime becomes just cos x times 1 plus y squared. There we go. You know, I'm just going to put brackets around cos x, just to make it clear that 1 plus y squared is not inside the cosine function. Otherwise, it's not entirely clear. And so, a perfect example of something that, again, may have seemed like it was going to be a lot of work, but you really can't, it's hard to really tell how much work there is by a quick little glance at it. And notice really most of this lesson was really focused on understanding and working with the derivatives of these inverse trigonometric functions. And to finish off, please try to get to the habit of sooner than later memorizing these three derivatives. They're all quite straightforward, actually, especially arctan of x. And they become really, really important, actually, when dealing with integrals.